breaking the gauge symmetry badly. And restoring gauge symmetries is an important point here. And this prescription, this curvature prescription, I mean, including curvature into the game, seems at least has a symmetry motivation. It has a symmetry reason. Well, I can tell you confidently that gravity is an induced force due to symmetry reason, and it is existing in the effective standard model, the effective field theory of standard model. I mean, you know, we are understanding its whole nature in effective field theory, not in any other picture. Even at CERN, I mean, we are testing effective standard model. That I can tell you. I know it is a little bit, how to say, it's somehow radical, but I mean, how to say, given this scenario, given this experimental situation, I cannot know, I mean, I don't know how to deal with this problem in a, how to say, in a smooth way. I don't know. Okay, I don't know such a way.
As far as I know, the geometrical coupling is through the first person to do this called Uchiyama. Uchiyama, yes, a Japanese man, which involved even the young Mills coupling. Stuckelberg's was a very special case.
I see. You say that Uchiyama generalized Stuckelberg's?
I think that is the most general case.
Oh, I'm sorry, because I didn't know that.
He did it for tensor fields, and then in the 1950s, Young Mills, famous, came with nonlinear vector coupling. Now you are introducing gravity as boson-like.
Curvature, let's say. Not gravity, but curvature as a boson-like, yeah, it's introduced.
The carrier of is that it must stay massless. So
it is classical, so it gives you Fourier completion, needed Fourier completion.
So naturally, it should be a tensor coupling in what I can feel. In high energy physics, they do on vectors all the time.
Yeah.
These covariant gauge derivatives.
Yeah. We do only with the vectors because tensors are too difficult and we don't have a tensor particle around. At CERN, for example, they say that, at least some people, I heard from some people that the next particle to be found is a spin-triad particle. And spin-triad particle is a new fermion, and its couplings are, awkward couplings, and Jana and Ozan, they are working on it, and it's an awkward theory.
Rarity-Schwinger.
Yeah, Rarity-Schwinger reality. Not in the sense of gravity, but not in the sense of gravity, no, but as a general, fundamental spin-triad field. They say that this is important. I don't know, I'm not sure. But according to my construction, new bosons are needed. That's all I can tell you. But the point is that these bosons, not all these bosons are to interact with ourselves. Because even dark matter doesn't need to interact. In fact, phenomenologically, we see that dark matter is not interacting with ourselves, at least for cross-sections down to 10 to minus 49 centimeters squares. Crazy small cross-sections. Anyways, this is, I don't know,
Well, of course, we did not work on such models. What we worked was that transfer of frames, Jordan, Einstein, that brings us some scalar fields automatically, a complicated potential function, that finding exact solutions there always a big headache. We have some, mostly in 2+1 dimensions, we have exact solutions for some special cases. don't know the method that you are following, how strong it is.
This is a mixture of field theory and gravity, and even suggesting a referee to the journal is very difficult because you have to have a person who knows both fields. And anyways, and you are suggesting some things, but it's difficult. I'm mainly a particle guy. I mean, I'm a particle physicist. I'm a gravity guy. I'm not interested in solving Einstein's equation or finding a different metric solution, blah, blah. They are outside of my interest and my knowledge. I cannot do that. However, from particle physics point of view, as far as I understand, as far as I can tell you, at least the results at CERN experiments tell us that we are in a difficult time. We are in a difficult time in understanding nature. Either this spontaneously broken gauge field theory logic is wholly wrong for some reason, and we will invent a completely new paradigm about which I have no idea, no imagination, or we have to keep quantum field theory as our working mechanism, and we have to find a mechanism like mine here to make things work. You can ask me how you introduce gravity, why you introduce it. I can tell you just one answer. It works. This is the only answer I can tell you. It works. Because if you don't want to, if you are not to introduce any new particles, new forces into the system, what can you do to make it standard model? Except for gravity, what can you do?
If we increase the dimensions, for example,
if we increase dimensions, when we look at from 4 dimensions, we see that those dimensions appear as a tower of massive particles. We have to find those particles at the colliders. Colliders tell us that there are no such particles. Even in the year 2003, people were making sure that extra dimensions do not exist at all. Because corrections to electroweak observables were too large to admit already at that time. I remember I was at the end of my postdoc term in the United States, and people were feeling like that. But people were hoping somehow extra-dimensional black holes to appear as a new dimension to physics, because it would also motivate gravity. It would be a very rich field to my idea, but it didn't come out. Even at CERN, I remember in 2003, people were marching with their slogans. We hate black holes, we don't want black holes. Maybe it was a joke, but people were marching. I remember such pictures. I was in the US, but I saw such pictures from the marching.
And higher dimension is one way to sweep the dirt under the carpet.
Yes, you're right.
But it has a beauty that you may start from a higher dimensional space. Just you have gravity, but nothing else. Watch it. You come one dimension less.
Yes.
Automatically, you see that there are physical fields created.
Yes.
So, and everything goes consistent. This is how the dilaton and electromagnetic fields are created from higher dimensions. So, this is the Kaluza-Klein theory that works perfectly. And I learned that Klein was a man that he learned everything from reading, even swimming.
Even swimming?
Yes.
I'm not able to swim.
He never attempted to swim in water. He read from the book how you will swim, and then after he read, he went and he started swimming. And it is a very beautiful theory, this Kaluza-Klein. But the question comes when you combine it with your Higgs forms and standard model, which are too involved. that so much diversities arise in this reduction of dimensions. So I had to solve the problem once, I remember. In 5 dimensions, I have only pure gravity, vacuum. Then, when I reduce lower dimensions, I see the emergence of a field Lagrangian, so a number of physical fields. And if you continue reduction further, I think these have all been worked out, you see some richness of new fields. But coming to masses, you know, mass terms always have difficult problems with gravitation. So you face problem there.
Right. Extra dimensions. I was working on it, I remember. It was very appealing, but standard model is a, I remember John Byers was commenting in some page recently. He was saying that how such an ugly theory is working such nicely. I hate this standard model, he was saying. Something like this, not these words, but similar to these. It's indeed interesting when we couple. For example, Nima Arkan-Ahmed worked for years for this naturalness, and he found n equals 8 supersymmetry, which has only one unknown coupling, was able to admit a representation in which you give up space-time where all these divergences exist. You give up all these and you go to a, how to say, model space in which you are able to deal with all quantum amplitudes in this field space. So you don't have any divergences because you get rid of space-time. So existence is somehow transformed from space-time to some other region or some other place. But he realized after all those work that this works only in n equals 8 supersymmetry. It doesn't work in another theory, especially it doesn't work, in no way works with standard model. Because standard model is so strong, everything is measured and everything is known, and there is no such symmetry as n equals 8 or something supersymmetry. It's gone.
But maybe we are not doing extra dimensions in every scale in local frame, but and somewhat there are some brains and connected to our universe. Mm-hmm. For example, like Arkan-Ahmed model, at the large scale there are extra dimensions. Mm-hmm. So we can detect as in the particle colliders. So if there are some extra dimensions, but for the higher energies.
Yeah, I mean, he's suggesting that 100 TeV collider will detect, let's say, 6% or no, 10 to minus 6 fine-tuning. They will test it. But I don't know. If you go to higher energies, your background in the collisions is also increasing. It's not a dramatic, I mean. Some certain new channels can open, and there's a new particle, it comes into collider range, it gives a bump, and that's good. But otherwise, your background is also rising with the higher energy. You produce as many as new particles, the background. So higher energy is good, but higher luminosity is also good. It's also necessary. Luminosity.
For example, we are now living in 4-dimensional universe. Mm-hmm. But at the surface of the black hole is 3-dimensional. Mm-hmm. But when we go inside the black hole, maybe the dimensions are reduced to the number 1. At some point, we come to the dot. Like a Big Bang model or universe model.
You mean you want to decrease dimensions?
Yes, maybe in the black hole or in some system in the universe, the dimension is decreasing, but outside we are living in 4 dimensions. Maybe after 1, it's also increasing from the Planck scale.
I see.
I guess.
I never thought about decreasing dimensions. I don't know that.
In this case, how you make a wormhole in 3 dimensions?
I don't know. we can, I think we have some tools to connect 4-dimensional. If we can do connect the 4-dimensional classical mechanics with 3-dimensional, for example, wormhole, black hole, we can do it, but it's not easy because dimensions are not equal. But for black hole case, wormhole case, we have a throat, we have a 4-dimensional black hole. We use the 3-dimensional surface of this rod and
Maybe
we
you
connect
can
it.
check this. I'm not sure. I'm not an expert, but Horava gravity. Horava's gravity relativity is broken. He's distinguishing time and space. Remember? At very high energies, instead of this relativity, he distinguishes between space and time, let's say. They transform differently. Maybe it is the starting way. I mean, since you start distinguishing between space and time, you can do different things to different things in this case.
Yeah.
Maybe it is the starting point. I don't know. I mean, your question just reminds me that. I don't know, but I'm not sure. I didn't work on Horava gravity.
No, it violates Lorentz invariance.
Yeah.
So light does not follow the cone.
Cone is broken.
Yeah, so, but to go further, Richard Feynman had expressed that I do not believe in this spontaneous ray symmetry.
Richard Feynman.
Yes. He found it rather artificial.
Ah.
Yes. And it works, of course, to a certain extent. It has a working area, but to what extent you need more space and more higher dimensional space and so on. And it is like embedding any Riemannian geometry that they give you. You can find a higher dimensional Euclidean space that you can embed it. In fact, this method was the first that the high energy physicists enjoyed, because when they wanted to extend their formalism to curved space, so they said if we start from an Euclidean space, let us say dimension 10, and you go down, then by embedding methods, always you can embed a lower dimensional curved space into a higher dimensional flat space.
Yes, I know.
So this,
there have been such models.
yes, this is a good model. In fact,
I was actually intending to work on it with Gregory Gabadadze, I remember. Maybe I'm wrong. He can forgive me if I'm wrong. And at that time, he was suggesting, this was his suggestion actually, at that time, that these curved spaces can be embedded into flat high dimensional spaces. But at that point, I think the difficulty was that under quantum corrections, the structure was not stable. I remember such a thing. But you can ask me what quantum correction. I mean, I'm constructing the geometry. In that sense, you are right, but I don't know. I remember.
It was, I think, in 1962 something, there was a high energy conference in the United States. Someone by the name Friedman, he organized all those kind of mappings from curved spaces to flat spaces, and the high energy physicists enjoyed that conference very much. I just read about it later on.
I see.
So maybe you, if you are interested, you may follow
I can
that
look
way.
at it.
Yes.
Here also in your wormhole, you are connecting two flat space times. Not necessarily flat,
It
but
can be flat. It can be flat, but the connection, let us say ring, it is not flat.
I know. I would say that point. I mean, near the connecting region, near the, let's say, hole, of course, space-time is not flat, but in principle, you can connect two flat regions, you can say.
Yes.
So,
Yes.
asymptotically flat regions. This is much better. Okay, asymptotically flat regions.
Yes.
Yes, you can connect.
Dually, and his group make a DGP gravity
Yes.
by connecting two brains.
Yeah, they kinetic job also on the brain. Yeah.
Also doing in particle.
Yeah, it was very important for particle physics. People have done this cosmology, they calculated this non-perturbativity rate, scale, etc. I remember people have done a lot on that. Can you ask me something?
I have two questions. One is about the scalars in your action. You suggest scalar fields for new physics. Is it possible to vector?
Yeah. There can exist everything. And just to give you a worst example, I mean most dangerous field, I put scalar field because it is dangerous always.
As an example.
As an example.
And the other one is when we look at from the particle physics part, is it normal to consider conformal invariance? Because the particle physics after spontaneous symmetry breaking, there are massive particles, dimension full, constant, and it is not normal to consider conformal invariance.
In reality it doesn't exist. But people were imagining that at high energies maybe everything is conformal. And in for this naturalness problem, some people suggested that. And I think some people calculated it and they found that Higgs boson mass was getting corrections proportional to the scale at which conformal symmetry is broken. So it doesn't matter, I mean, you should break conformal symmetry right at the Fermi scale to be able to save your theory. If you go higher, then there are corrections in proportion to that scale. It kills your model again. It's, I mean, stabilizing Higgs sector, stabilizing vector sector, stabilizing vacuum is a very big deal here in pure theoretic point of view.
Just some simple questions I want to understand. First of all, new physics is unavoidable.
Yeah, as far as I see, yeah.
Unavoidable, and the suggestion is clear in natural theory. 250 GeV is, if it is interacting with the standard model, it should be
around that scale.
Around that scale. So, for example, if you try to, let's have that 750 GeV bound there, and we have a need to explain new physics and applying the S scale for the theory, then will it create some trouble in your model in terms of naturalness?
No. I'm saying that around the first scale, since the correction is logarithmic and since there is this loop factor, etc. in front, 750 GeV is okay. I mean, even 2 TeV is okay.
I see.
Because the connection is logarithmic. I mean, the factor in front is logarithmic, but it is proportional to the new physics scale. It is dangerous. That was, GNP to minus 1 and whatever. But there is a 1/4 pi squared in front. There is a coupling squared in front also. So the correction doesn't exceed that amount.
Then, for example, for the dark matter case, there is experiments there, and definitely what you want to have is again at most around, let's say, 1 TeV particles. The idea is, for example, even in the standard model case, if there is some new particle, the search was what I mean very weakly coupled things should exist in your perspective. Right? High luminosity is important in a sense.
Right, no energy. There are two ranges, you are right. Either coupling is strong and mass is small, this can happen, or mass is large or coupling is weak. There are such compromising situations in this search. At the LHC, we are searching for large masses, that range. And we are hoping that coupling will be strong enough to appear, to give some signal. But there is also the low mass range, GeV, MEV, KeV range. In that case, coupling is very small, unbelievably small, so the particle, a light particle is admitted in this system. It can exist also.
And if there is a standard model interaction, let's say, they are separated, your new physics, and it will be forever dark, right?
It should be forever dark. That's what I'm saying. They should not couple other except for gravity. gravity, they can couple this. Of course, gravity is universal in both sectors. But other than that, they should not have any. For example, I was imagining SU6, SU7, SU10 type gauge theories are good. Okay, I mean, they give you enough.
Yeah, the thing is, it is so interesting. There is a strong need for new physics, but that new physics, if it does not interact around 250 GeV, no hope to see new physics.
Well, this is how to say. Of course, if you find some other mechanism, then you can say that, well, I can have, for example, 100 TeV particle, and my theory is natural. Okay, well, you can live with it. But according to this picture, the end result is that if new physics is interacting with the standard model, there are some logarithmically unnatural contributions to Higgs boson mass. Of course, the same contributions exist also for the new physics particles. They are also getting those contributions from standard model rules. You cannot avoid that. The other particles also are getting a correction to its mass from standard model, of course. Correction is logarithmic, so you can live with logarithmic corrections. However, correction is proportional to the new physics scale. That is dangerous. And in this sense, what I am concluding is that if new physics is to exist, it should be around this weak scale, electroweak scale, where, well, I cannot give you a number, but it should be around this scale. That's what I'm telling you. I mean, in this scenario, I would not expect, or I would not be able to motivate a particle at 100 TeV. I would not be able to motivate it. I would not be able to say that, well, let's put a particle here. I have no motivation for that. I cannot say. If it is unobservable, of course it can exist everywhere.
Good, higher.